All right, we're just over halfway through this first introductory chapter. And I want to take a look at two big ideas today. We're going to revisit functions and look specifically at domains and ranges. And I also want to start looking at the cone problem. First of all, remember that we've been talking about functions as, I like this idea of a function machine, that here I have the function a, and I'm going to take certain x values and throw them into the function machine, and what's going to come out, a is going to do its thing to it and spit out a of x. Now, a is this very specialized machine that only allows certain numbers to be thrown into the machine. All of those numbers are called the domain, and we would list it like this. The domain of a is a set. So that's why we would use these braces instead of parentheses or square brackets. But the domain of a is going to be all of the inputs, all of the x's that can be thrown into the function. And in this case, we've got all of our x's right here as the first number in every ordered pair. So we'll have 2, -3, 0, and 1. And that's the same thing as putting them in order too, -3, 0, 1, and 2. Right? They're both technically correct. Neither one is wrong. Now, when we're talking about the range of a is going to be the set of all of the outputs, all of the numbers that come out of the function, so all of the y values. In this case, that would be 0, 1, -6, and 0. Now, it's okay to have a number repeated in the range. That's okay. It would not be okay to have element of the domain repeated. In that case, it's not a function. But when we're writing out the range, it's okay to put it in order. So -6, 0, and 1. Notice that when I'm rewriting it, I didn't write 0 twice. You don't have to show that. 0 is an element of the range. We don't express how many times it shows up. A lot of times it's real easy to identify the domain and range when you're looking at a graph of the function. Now, I don't even have this function labeled as anything, so I can't call it f or g or anything like that. But I can identify the domain and the range by looking at the span of the graph in the x direction and in the y direction. Remember, the domain is talking about all of the x's. So when I think about this function, I'm really looking at, like, how far does it stretch to the left and to the right? You know, as we move around this function, if we think about a point moving to the right or moving to the left, are there any x values that we can't use? And since this function is continuous, there's no breaks in it, there's no asymptotes or anything like that. The arrows signal that it's going to continue in this way to the left and the right. That would mean that the domain is all real numbers. So you can abbreviate it like that, or if you would like to use the set notation of this, like double R, you know, that's good too. Similarly, when we're talking about the range, that's going to be the set of all the outputs, all of the y values. So we look along the y-axis and think about our function, all the points that are on this function. You know, as we move along, you know, we're going to continue to go up all the way, continue to go down all the way, and we're not going to have any breaks, jumps, asymptotes, holes, anything like that. So the range for this function is also all real numbers. Here we have a nice parabola. Thinking about the domain, look along the x direction and this function. As we move around the x, there's no breaks or holes or anything moving left to right. We can use every x value when we plug it into this function. We know it's a parabola. It's going to be a quadratic function, and we can square any positive and negative numbers, zeros, decimals, fractions, everything. So our domain, again, is going to be all real numbers. Now, when we look at the range, this is where we have a little bit of a difference, because as we look along the y-axis, our y values start at this 1 and continue up. That we don't have any y values that are going to be, a half or 0 or any negative numbers, anything like that. So when you are identifying the range, you have to first of all make sure that you're talking about the right variable. In this case, we can assume that every ordered pair is in the form xy. So when we're talking about the range, that's going to be the y coordinates. And we say that the y's have to be greater than or equal to 1. If you wanted to use interval notation, you would say that y is an element of the set that includes 1 and goes up to infinity. Now we got one that's messed up. It looks like kind of like an absolute value type of function, but it's very limited. It doesn't go on forever in either direction. So when we think about the domain, just look in the x direction. There are points start here at -2 and end at 1. So we can say that our x's are in between -2 and 1. We do not get to include -2 because there's the circle at the end. But we do get to include 1 because it's a closed circle, that dot. Very, very important to make sure that when you're talking about the domain, your variable is x. Now when we're looking at the range, the lowest point in our range is down here at -1, and our highest point goes up to 3. So our range is going to go from -1 to 3. We're talking about y coordinates. We do get to include -1 because that's not a hole down there. That point is there. But we do not get to include 3 because of the circle again. Here we have another unique situation, this step function. And when we're thinking about domain, remember, we're going along the x-axis. And since we can think about points, starting down here, and we're going to continue until we get to -1, x being -1. And then we have this hole. But immediately at -1, it is defined because we jump up here and continue along this part of the curve until we get to the end, where we jump up again and continue along till we hit the end, jump up and continue along. So as we look along the x-axis, we see it's defined right here. That's for this part. Then we jump up to the next step, and the next step, and the next step as we move along. Right? So all of those x values are defined. They're all used when we start down here at -2 and go up to +2. So all of my x's are going to be between -2 and +2. We do get to include -2 because of the dot. However, we don't get to include +2 because of the circle. So that's going to be our domain. Now, when we're talking about the range, this is a lot trickier because on this first section from -2 to -1, all of those y values are right here at -2. On the next step from -1 to 0, all those values are at -1. And the next step is at 0, and the next step is at +1. We do not get to include all of those decimal values in between there. We actually only get to include 4 points. So we can say that the range is the set of numbers, -2, -1, 0, and 1. All right. You can't say that y goes from -2 to +1 because it doesn't include all of those values. It actually only includes 4 very specific values. So last one of these graphing ones, but now I've only got 4 points that are identified. So very similar to like the range in the last example. As we look at the domain, I want to know the x value at each of these points. And so as I look along the x-axis, I see that I've got an x value here at -1. I've got one here at 0, one here at +1, and at +2. So our domain is going to be the set -1, 0, 1, and 2. When we're looking at the range, then we look along the y-axis or in the y direction, and our bottom point matches up with -2 on the y-axis. We have this x-intercept, so that has corresponds to a y value of 0. This y-intercept is at 1, and our last point has a y-coordinate of 2, which means our range is going to be the set of numbers -2, 0, 1, and 2. So how about when we see functions written as functional notation, as equations? How are we going to identify the domain and range for those? Well, you have to think about what they look like. For instance, here f of x equals 1/2 times the quantity x minus 5. Well, we know that's a line. It's got a slope of 1/2. So I'm talking about this, it goes through, it has an x-intercept at 5 and a slope of 1/2 like this. So here we have a function that is continuous. There's no holes or breaks in it at all. It's going to go left and right forever. It's going to go up and down forever. So we know the domain is all real numbers, and the range is all real numbers. Now, for g of x equals x squared plus 4x minus 5, we know that that's a parabola. We also know that it opens up. So I'm dealing with something like this. Right? Not exactly sure where it is right now. However, I do know that since it is a parabola, I can identify the domain pretty easily. The domain is going to be all real numbers because it goes left and right forever. However, the range is what we're going to have to figure out. So what do we know about parabolas? Right? You know a lot, actually, and you know how to find that vertex being the lowest point here. We know that the x-coordinate on the vertex of the parabola is -b over 2a. So in that case, in this case, it's -4 over 2 times 1, right? A, B, C. So we're looking at an x-coordinate of -2. So as a point here, the x-coordinate is -2, but that doesn't help us with the range. -2 is an element of the domain, though, which we knew already because the domain includes all real numbers. To find the y-coordinate, though, we just take -2 and plug it in. So g of -2 is going to be -2 squared plus 4 times -2 minus 5. So 4 minus 8 minus 5, that looks like -9 for our y-coordinate. Right? So we can say that our range, being the outputs, and technically in this case, since we know it's g, we could say g of x is going to be greater than or equal to -9. Let's take a look at a lot of other functions too and what we know about them. For instance, h of x is equal to square root of x minus 3. Since this is a square root, we know that anything under the square root, the radicand, has to be positive. So when I'm thinking about the domain, because what I have underneath there is in terms of x, I know that x minus 3 has to be greater than or equal to 0. Has to be positive. At the very least, it could be 0. You can find square root of 0. So if we were to solve this, that would mean that x is greater than or equal to 3. And that's our domain. When it comes to the range, as long as we have a valid x value that we can plug in there, we're going to take the square root of something. We're going to take the square root of a non-negative number. And any time that we take the square root of a non-negative number, we're going to get a value that's not negative. Right? Square root of 0 is 0. Square root of everything else is going to be positive, as long as we put a positive number in there. So our range is dealing with our outputs, the h of x's. Those have to be greater than or equal to 0. How about if we had capital H of x is equal to the square root of x minus 3? How does that change things when it comes to domain and range? Well, for our domain, that's talking about the x values, and x is the only thing that's underneath the square root. Right? And our radicand, what's under the square root, has to be greater than or equal to 0. But when it comes to our range, what comes out, that square root of x is always going to be greater than or equal to 0. So that would mean that square root of x minus 3 would be the same, would be greater than or equal to 0 minus 3. So our big H of x, our range would have to be greater than or equal to 0 minus 3, or -3. It's weird how sometimes the simplest types of functions cause the most headaches and the most confusion. When I have something like k of x is equal to 7, and we want to identify the domain and the range, think about what this function looks like. It's a horizontal line. It says that the y value is always 7. So if I were to graph it, it has a y-intercept up here at 7. And then if x is 2, y value is 7. If x is negative 3, y value is 7. And we end up with this horizontal line. So when we're identifying domain and range, the domain can go left and right. X values can go left and right forever. So our domain is going to be all real numbers. But what comes out is always 7. So we can say that k of x is equal to 7. That's the only value it's ever going to be. Now how about the exponential and logarithmic functions? If we deal with f of x first, 2 to the x power, and start graphing points, I know 2 to the 0 is 1, and 2 to the first is 2. 2 to the 1/2 is square root of 2, and it should come back to you that our graph looks like this. Right? We can plug any value of x into this function. If you look at just 2 to the x and think about just mechanically what can I put in there for a power, we can have positive powers. We can have negative powers. You can have 2 to the 0. 2 to the 0 is 1. You can even have fractions and decimals and stuff, and we will give values for all of them. So when we're talking about our domain, it can be all real numbers. Now, when we're talking about the range, however, notice that what comes out of it, right? 2 to any power. If we start with a positive base and take it to a power, we're going to get a positive number. Right? So our y values, capital F of x, has to be greater than 0. Ask yourself, though, can it equal 0? Well, can you take 2 to a power and get it to be 0? No, we can't. And if we look at the graph, we see that horizontal asymptote there as the x-axis. So our range is just that f of x is greater than 0, but not equal to. Similarly, when we're talking about the natural log function, remember that the natural log is the inverse of the exponential. So just like our exponential function starts small and then grows, and what I mean by that is that when x is very small, y is very small. Same thing's going to happen here, except we're going to switch those around, that when y is very small, x is very small too, but not negative. Right? And when y is 0, then we end up with a value of 1, and we get this curve that's going to be the inverse of our exponential function. And looking at domain and range now, the domain is what's going to be greater than 0, but not equal to. And when we're talking about the range, that's where we see the function can go down forever and up forever. So our range is all real numbers. How about some rational functions? Like h of x is equal to 1 over x plus 4. If I'm thinking about domain, the only thing that I have to worry about when it comes to a rational function is getting 0 in the denominator. So x plus 4 cannot equal 0. And solving this just by subtracting 4 from both sides, we get that it means x cannot equal negative 4. And that's our domain. X can be any other real number. It just can't be negative 4. And what about the range? Well, when we're just looking at the fraction itself, 1 over x plus 4, as long as that denominator is not 0, 1 over anything is going to be some number, but it's not going to equal 0. If we have 1 in the numerator, this fraction can never, ever equal 0. So h of x cannot equal 0. That's why when we look at the graph, we're going to have this vertical asymptote over here at negative 4. And we're going to have a horizontal asymptote along the x-axis. And we get our curve, if you remember, to look like this. So now, how about k of x when it equals x plus 3 over x plus 4? So we have that same denominator, But now our numerator can equal 0, so how's that going to mess with everything? Well, first of all, taking a look at the domain, the only thing we have to worry about with the rational function is that the denominator does not equal 0. So just like before, our domain is that x can't be -4. Now, when it comes to the range, this is still a rational function. We're still going to have some horizontal asymptote. And I don't know if you remember this from pre-calculus, but to find out what that horizontal asymptote is going to be, you just look at leading coefficients. Right? When they are the same, x over x, we just simplify that. So that our range is going to be k of x cannot equal x over x, which is 1. So when we're dealing with rational functions, it's our denominator that's going to give us our domain, and it's the leading coefficients that's going to help us identify the range. All right, one last function, L of x is equal to the square root of 4 minus x squared. This one is a very, very special kind of function. We can go through and look at the domain, just like we had before. When it comes to our domain, we're dealing with square root function, so the radicand, that 4 minus x squared, has to be greater than or equal to 0. And now when we start solving, I'm going to add x squared to both sides, so 4 has to be greater than or equal to x squared. If I rearrange things, x squared is less than or equal to 4, which is not a problem. And now we go through and square root. And here's something where a lot of your teachers that came before you maybe lied to you. All right? They said that when we take the square root of x squared, the square root and the squared, it cancel, and you're left with x less than or equal to square root of 4 is 2. However, that's not true. And we can see that it's not true if we just let x be -3. That's definitely less than 2, right? However, if I were to plug that in, L of -3, that would be the square root of 4 minus -3 squared. So 4 minus 9 is -5. And that's going to be a non-real number. So -3 is not part of the domain. Now, the reason that that doesn't work is because square root of x squared is not x. It's actually the absolute value of x. Then when we get rid of the absolute value, we create this compound inequality that x has to be in between -2 and +2. Now, when we're talking about the range, there's another interesting thing that happens. We are certain that L of x has to be greater than or equal to 0. I mean, we're talking about a square root function. Square root function is greater than or equal to 0. However, it doesn't go all the way up. Right? You're not going to get a value of positive 100 or anything like that. And we could check that by testing some points. Right? If I were to graph this out, using elements of our domain, plug in -2, right? L of -2 is going to be the square root of 4 minus -2 squared. -2 squared is 4, 4 minus 4 is 0, so we get square root of 0, and that's going to be 0. So at -2, we're at 0. And it should be easy to see that at +2, same thing happens. We'll also get 0. So over here, we get 0. But what if we try a couple other points, like positive or -1? Then when we plug that in, we'll have square root of 4 minus plus or minus 1 squared is 1. So we'll have square root of 3, which is like 1.7. So about right here and here. And how about L of 0? That's going to be the square root of 4 minus 0 squared. And square root of 4 is 2. And so we see that what we're going to get is actually a semicircle. And that's what makes this one, this function L of x, so important, is that this is kind of the form for a semicircle. That what we have is the square root of the radius squared minus x squared. Right? And that gives us the top half. If this were the negative square root, it would give us the bottom half. So going back to the range, our range is not that L of x is greater than or equal to 0. It's that L of x is in between 0 and 2. And we can include both of those endpoints. All right, last thing I want to look at is a problem that you're going to become very familiar with this year. It's called the cone problem. And it has to deal with this conical tank. And what we have is a situation where the cone is not filled all the way to the top. It's only filled up to this height, right here. So all of the stuff in the bottom is water, and you know, it's not filled up to the top. So how are we going to find the volume of just the water that's in the cone? Now, you're given the formula down here at the bottom, and I'll always give you the formula. You should probably have it memorized by the time that, that you get done with this course. So we can jump right to that, because I'm trying to find a volume of water. Volume is going to be 1/3 pi r squared times the height. Now, in part A, when we're looking at a height of 4 centimeters, what we're saying is that this height is 4 centimeters, which is great. So I could plug in 4 for the h. However, I don't know what the r is. Right? And that's where the tricky part comes. And in order to find out what that r is, the key to this problem is seeing that we have similar triangles right there, and then that triangle is going to be similar to this triangle in green. Right? So we have to do a little side calculation first that when it comes to similar triangles, the ratio of corresponding sides is the same. So if I went radius and radius, those two are related to each other. 2 is related to r in the same way that the big height is related to the small height. So the big height is 10 and the small height is 4. So in this case, we can cross multiply. 8 is equal to 10r, divide both sides by 10, and we get that r is equal to 4/5. So we can plug that in there, 4/5. Now it's all about just calculating. So to calculate, we've got 1/3 of pi is pi thirds. 4/5 squared is 16/25. And then we still have this 4. So 4/1. And we multiply it all out. 16 times 4 is 64. 3 times 25 is 75. So I got 64 pi over 75. That's the volume, which is centimeters cubed. How about if we generalize it to a height of h centimeters? So it can have any height, not specifically 4, but anything. Again, our key is going to happen with those similar triangles, that 2 is related to r in the same way that 10 is related to whatever height we're going to fill it to, h. So you're going to see me ask a lot for you to first find r in terms of h. And so we'll need to calculate that as cross multiply. 2h is equal to 10r. Divide both sides by 10. And we get that r is equal to h over 5. That's going to be very important to us. When we want to now find the volume, we can find the volume in terms of h, because we'll have 1/3 pi r squared h. And our h is h, all right? That's the height. But our radius in terms of height is h over 5. Now when we calculate, I'll have pi over 3 times h squared over 25 times h. So pulling those h's out, we'll have pi over 75 times h cubed. And that'll end up being our volume. We can check that our first part over here, 64 pi over 75, with our formula that we came up with, because we found out that our volume can be found just when we know what h is by plugging that height in. And h cubed is the 64, and that'll give us 64 pi over 75. But anyway, you'll get a lot of practice with this type of problem. Make sure that you keep asking questions in class. Otherwise, there you go.